another video tutorial from microbiology with Shalnik. So today we are going to take a very exciting series where we are going to discuss about the centrifugation chapter. Okay, so these topics are our topic of discussion. So first of all, we are going to discuss about preparative and analytical centrifugation. Then a new topic that we have not discussed previously, that is fixed angle and swinging bucket rotor. Then we are going to discuss about the RCF, that is relative centrifugal field, that is the strength of the field generated by different type of rotor and the speed at which we are operating the system. Along with, we are going to discuss about the V by omega squared R, that is our sedimentation coefficient. Then we are going to discuss about the three kind of centrifugation: differential centrifugation, where we are separating subcellular components. Another one, density gradient centrifugation. In density gradient, we are going to discuss about isopycnic centrifugation and red zonal centrifugation. Okay, so in case of red zonal centrifugation, you have your gradient before centrifugation, and in isopycnic centrifugation the gradient will be after centrifugation. Okay, so and the last one is ultracentrifugation. Okay, so although among those kind of things where we have already discussed about some topics in details earlier, so today we are going to take two new topic, that is fixed angle and swinging bucket rotor. Along with, we are going to revise the chapter also. So let's start. Let's start with the basic concept of centrifugation, that is what is centrifugation, what is the need of centrifugation. So centrifugation is nothing but, suppose you have a sample in which is sedimented, or suppose you have a sample which is suspended in a liquid medium. Okay, and now from that complex mixture that I have called as sample, you wanting to isolate one. Okay, so the process you can obtain if your mixture have differences in their size and shape is called centrifugation. Okay, so what is the centrifugation? Centrifugation is nothing but what we used to observe in case of gravitation, with the help of gravitational force. That means, suppose you have taken a glass of water and you kept it for some time, okay, by putting some small materials in it. Okay, so after some time you can find out that all the small materials are suspended at the bottom of the tube, right? So that is the centrifugation process too, but the actual funda is it will take a lot of time if you only rely on gravitational force. So that is the reason why, along with gravitational force, we are just employing another kind of force called centrifugal force with the help of centrifuge machine. Okay, this centrifugal force simply help the gravitational force to suspending the materials. That is the concept of centrifugation. Okay, so let's start. Centrifugation is a process that is used to separate or concentrate materials suspended in a liquid medium. It is a method to separate molecules based on their sedimentation rate. Under centrifugal field, it involves the use of the centrifugal force that I have told you for the sedimentation of molecule. So I hope you can understand, right, that centrifugation is a process that is used to separate or concentrate materials suspended in a liquid medium, right? It used the centrifugal force under the centrifugal field to separate your molecules or concentrate your molecule based on their differences in sedimentation rate. Okay, so centrifugation can be divided into two common parts. One is preparative centrifugation, another one is analytical centrifugation. Okay, so preparative centrifugation means it is used for separation of one type of material from a complex mixture. Okay, suppose you have A to E as a mixture. Okay, then you are wanting to isolate A from that A, B, C, D, E containing mixture. So this kind of centrifugation will be known as preparative centrifugation. Okay, and another kind of centrifugation, that is analytical centrifugation. This analytical centrifugation simply means you are willing to analyze what is in your sample, what are the molecular mass of the particles present in your sample. For those cases you have to take the help of analytical centrifugation. Okay, so we have completed our first topic, that is preparative and analytical centrifugation. Now let's move to the fixed angle and swinging bucket rotor type centrifugation. Although this is the kind of rotors that we are using during centrifugation. Okay, so let's start. So first one, this is the fixed angle rotor centrifugation. So fixed angle rotor is a kind of rotor where we are holding our sample, or you can say tube, at 45 degrees centigrade. Sorry, not 45 degrees centigrade. Here we are holding the tube at 45 degree angle in relation to the axis of the rotor. Okay, that means here our tube is in 45 degree angle with the axis of the rotor. Okay, that is the idea of fixed angle rotor. So what is the utility of that holding the tube at 45 degree angle? So here the path length is increases. Okay, that allow us to span the tube at a high speed. Okay, and the faster you move your tube, the faster your component will separate. That means with the help of fixed angle rotor, the centrifugation can be done at a smaller time, within some time. Okay, another important thing I want to mention you, that during this kind of rotation the particles are strike on the other side of the tube. Okay, as you can see that they are tilting at a certain angle, right? So during their movement the particles that are inside the tube will strike at one side. Okay, so unfortunately the side where they strike is the opposite direction of the direction of the force. Okay, so as a result, if some molecules do not slip down from that side, so they remain in that side of the rotor. Okay, as a result they are not pileted, because remember centrifugal force helping us to separate the molecules, right? So but here the particles inside the mixture are striking at the opposite side of the direction of the force. As a result, the particles that can slip down from that side of the tube to the bottom are only be pileted with the help of fixed angle rotor. Otherwise the remaining particle will remain at the side of the tube. Okay, they cannot be separated. Another one thing that I want to mention here, that is the Rmax. This Rmax we are going to see in case of relative centrifugal field, that is depending on the type of rotor we have used, the size of rotor we have used, and the speed at which we have operated our system, there can be different type of field, that is the centrifugal field. Okay, so that is why instead of considering the normal centrifugal formula, scientists thought to consider the Rmax value to bring a standardization. Okay, so in case of fixed angle rotor, the Rmax value is the distance up to the bottom of the tube, as you can see from the axis. Okay, so Rmax is the distance up to the bottom of the tube, both in case of fixed angle rotor and the swinging bucket rotor. So fixed angle rotor provide us faster separation by due to the increasing path length, as you can see, and here we are holding the tube at 45 degree angle in relation to the axis. okay. But here one problem is the particles are strike at other side of the tube. As a result, the direction of the force is not in that direction where our particles are actually residing. As a result, the particles have to slip down from that side to be pillated, otherwise they will remain there and do not be pillated, they are not be pillated, okay. As you can see, some particles remain there, okay. So that is why total pillation of the or total pillet obtained cannot be done with the help of fixed angle rotor. So here I have written, this rotor holds the sample tube at an angle of 45 degree centigrade 45 degree angle in relation to the axis of the rotor, and in this type of rotor the particles strike at the opposite side of the tube, that I have explained to you, of the tube, where the particles finally slide down and collected at the bottom of the tube, okay. That means for reaching to the bottom it have to slide down from that side on its own. The centrifugal force cannot help itself in that part, because however, as the direction of the force is different from the position of the tube, some particle might remain at the side of the tube, and they are faster than other type of rotor as the path length of the tube increase. This is very important point for the advantage of fixed angle rotor, okay. That is, you need to keep in your mind. So now another thing I want to mention you, that the term fixed, that means the angle at which the tube are holded in case of fixed angle rotor is fixed, that is 45 degree centigrade, but you may not get a fixed angle in case of swinging bucket rotor, okay. That is the term swinging. So here the tube will be at 90 degree angle when the rotor starts swinging and when the process will start, okay. That is why here the tubes are suspended in a rack so that they can easily moved to acquire themselves at horizontal position, okay. As you can see, tubes are suspended in that kind of racks. So in this type of rotor, particles are present along the direction of the path of the force. So the drawbacks that we are facing in case of fixed angle rotor is solved by our swinging bucket rotor, because here our particles are actually in the direction or in the path of the force, okay, that allow the particle to be moved away from the rotor towards the bottom tube, okay. So good separation can be obtained with the help of swimming bucket rotor. Along with that, because of the tube remain horizontal, the supernatant, suppose here most of the tube remain horizontal, right. So supernatant remain flat in the surface, so it is easy to remove the remaining particles, that is deposited particles, from the supernatant, okay. So that is the concept behind the swinging bucket rotor and the fixed angle rotor. In fixed angle rotor, we are holding our tube at 45 degree angle in relation to the axis, and here the main problem is the particles are strike at the opposite side of the tube. As a result, the centrifugal force cannot help them to come out from the side to the bottom of the tube, okay. They have to slide down for their own, okay. And another important thing, that is the advantage part of the fixed angle rotor, is they are faster than any kind of rotor, okay. And that is the disadvantage of swimming bucket rotor too, that swimming bucket rotor cannot be as fast as our fixed angle rotor, okay. So in case of swinging bucket rotor, the tube acquire 90-degree angle or become horizontal during their rotation. That is why here tubes are suspended in a rack so that they can move enough and acquire the horizontal position. Okay, now in this type of rotor, particles are present along the direction of the path that force those kind of particles to move down to the bottom of the tube. Okay, so here a pure pellet formation, or if you want to concentrate your sample, you can opt swinging bucket rotor for your purpose. Now because the tube remain horizontal, so separation of the deposited particle from the supernatant is easy, because our supernatant in the swinging bucket rotor remain flat. Okay, so if you want to construct a difference between fixed angle rotor and swinging bucket rotor, so first thing that you have to write that in case of the fixed angle rotor, the tube angle or the tube is hold at 45-degree angle, and in case of our swinging bucket rotor, the angle is 90-degree. Okay, and in case of fixed angle rotor, it provides you fast separation than any kind of the rotor. Okay, and in case of swinging bucket rotor, the separation is slower than the fixed angle rotor. Okay, in case of fixed angle rotor, all particles may not be pelleted at the bottom, because here the position of the particles is opposite to the direction of the force, right? But in case of swinging bucket rotor, all of the particles move down to the bottom of the tube because of the force. Okay, so that is a difference between fixed angle rotor and swinging bucket rotor. So I hope you have understand about the concept of the fixed angle rotor and our swinging bucket rotor. So we have completed preparative analytical centrifugation, fixed angle swinging bucket rotor. Now let's come to the part of RCF. So in preparative centrifugation, we have learned that preparative centrifugation helps us in isolation. It isolates a particular type of material from a mixture of the sample. Analytical centrifugation helps us in analysis of the particles of the mixture. In fixed angle rotor, we are holding our tube at 45-degree angle to the axis, and in swinging bucket rotor, we are holding our tube max to max at 90-degree angle. Okay, so in case of fixed angle rotor, total pellet formation of the sample is not possible. Okay, because some of the particle may remain at the side, because the position of the particle is exactly opposite of the direction of the force. But in case of swinging bucket rotor, the position of the particles and the direction of the force is in same. That is why the force can help us to pellet all kind of materials. Okay, but fixed angle rotor gives you a faster separation, whereas swinging bucket rotor cannot give you that much faster separation. Okay, now let's talk about relative centrifugal field. So I want to explain about relative centrifugal field in that way. Let's try to understand that the size of the various kind of rotor may differ, right? And suppose you have run a centrifuge at 5000 rpm. Okay, and I have run a centrifuge at 10,000 rpm. So the centrifugal field generated in your case will be obviously different from the centrifugal field generated in my case, right? So in both the cases, if we are handling a same sample, so the separation result may differ, isn't it? That is the concept of relative centrifugal field. That is why the term relative is attached with the centrifugal field, because it is totally depending on the type of rotor we are using and the experimental condition, right? That means at what operating speed we are manipulating. So relative centrifugal field describes and compare the strength of the field generated by different size of the rotor and different operating speed. Okay, it is expressed in multiples of the gravitational force, abbreviated G. That is the important thing, because at the very first starting of the video I have told you that centrifugal force is nothing but it helps our gravitational force, right? So centrifugal field will be explained as the abbreviation of the gravitational field, okay, or as the multiplication of the gravitational field. That means you may get relative centrifugal field value as 5000 G, suppose. Okay, so relative centrifugal field compares the strength of the field generated by different size rotor and at different operating speed. Okay, so it is a comparative term. So RCF is depending on, so we can determine RCF with the help of R omega square G. Okay, that means the RCF generated by a rotor depending on the type of the speed of the rotor in revolution per minute, that is our omega, angular acceleration. Another one is the radius of the rotation. Okay, so that is the formula. So and we will use G also, that is our 980. So angular velocity omega is also can be expressed as 2 pi rpm by 60 rad per second. So if we put that value here, then we ultimately get this one. That is the formula you need to remember to find out the value of RCF. But I recommend you to just remember this one and remember this one. So then it will be easy to you to derive. Otherwise, this formula is quite tricky to remember. You may forget about what is at the 10 to the power, right? Either it is -4 or -3 or -5. It is -5, and is it was 1.2 or 1.12, right? So instead of doing this, I would recommend you to just remember this one and place 2 pi rpm 60 here, and in place of G you have to place 980. Okay, then you can get that one. So now that I have mentioned you during the fixed angle rotor explanation that there is a term Rmax. Okay, now what is the requirement of this Rmax? So just try to focus on that formula. So now, as the entire centrifugal field is totally relative, if we want to standardize something, because it is totally depending on the type of the rotor we have used and the operating speed, right? So we have to either look for the maximum value or either look for the minimum value so that we can standardize, right? So here the only thing that can be constant if we consider maximum or minimum, that is the small r, because rpm has no upper limit, right? We can use any kind of speed to rotate, right? So instead of that we choose small r for that standardization. Okay, and the maximum value of small r is taken, which is in case of angular or fixed angle or swinging bucket rotor is from the center to the bottom of the centrifuge tube. Okay, and in case of upright one, it is from the center to the outward of the tube, outwall of the tube. Okay, the distance from the center to the outwall of the tube in case of upright one. Another one, that is angular or swinging bucket rotor, the Rmax value is the distance from the center to the bottom of the tube. Okay, that is the concept of Rmax. What is the requirement of Rmax? So relative centrifugal field, what do you mean by relative centrifugal field? Relative centrifugal field compares the strength of the field generated by different size of rotor and the speed, different operating speed at which we are operating our system. So it is expressed in multiple sub G. So RCF generated by the rotor is depending on the type of the amount of the speed, that is in rad per second, and the radius of the rotation. Okay, and that is RCF is equal to R omega square by G. So we have derived from R omega square by G this one by putting omega is equal to 2 pi rpm by 60 in rad per second unit. Then we have understood about R max concept, that is in case of angular or swinging bucket rotor is the distance from the center to the bottom of the tube, and in case of upright one it is the distance from the center to the outer wall of the tube. Okay, so that is the concept behind relative centrifugal field. I am again explaining, it is nothing but a comparative study of different centrifugal field, the strength of the different centrifugal field generated by different type of the rotors. The size of the rotors is the variable term here, and the operating speed at which we are operating our system, and it is abbreviated as the multiple sub G. So if you get any kind of mathematical question from centrifugation, then you can get relative centrifugal field as something like that, 5000 G or 4000 G. Okay, it will always be expressed as multiple sub G, and RCF generated by a rotor depends on the speed of the rotor at which it is operating and the distance from the center to the rotation, that is the radius of the rotation, right, that is small r omega square by G. From that one, by putting omega is equal to 2 pi rpm by 60 and by putting G is equal to 980, we can get our desired formula. Okay, and here we have learned what is the significance of R max, that is in case of angular or swinging bucket rotor is the distance from the center to the bottom of the tube, and in case of your upright one it is the distance from the center to the outer wall of the tube. Okay, now let's move to the next topic. So up to that part we have learnt about preparative and analytical centrifugation. Preparative and centrifugation help us to isolate. Analytical centrifugation help us in analysis. Fixed angle bucket rotor, where we are holding our tube at 45 degrees centigrade, it provides us faster separation, but it cannot ensure the pellet formation of the entire sample, because some of the sample may be remain in the side. Okay, those kind of molecules that successfully slip down from the side are pelleted at the bottom, otherwise not, because here the direction of the force is opposite to the direction of the position. And the opposite case in case of swimming bucket rotor, where tubes are holding, we are holding our tubes at 90 degree centigrade, 90 degree angle, and here despite we are not providing that much of speed that we have provided in case of fixed angle rotor, but swimming bucket rotor allow us to pellet our entire sample, right, because here our position of the sample is exactly in the direction of our force. So RCF value then we have discussed, that is the comparative study, smaller omega square by G. Now let's come to the sedimentation coefficient topic. Although in this topic I am not going to derive the mathematical equation, I am just explaining you the concept regarding the sedimentation coefficient. Okay, although we have launched various kind of video regarding the principle of centrifugation, where we have derived how sedimentation coefficient can be derived. Okay, so you can watch those videos to understand how you can derive the sedimentation coefficient. So now let's look those formulas. So let's start. So the first thing that I want to explain you, that we have to first discuss about the centrifugal force. That means in the tube where you have your solution containing mixture of particles, it is the force that is acting on each of the particle. Okay, if you are spinning your tube in a centrifuge machine. So here m is the mass of that particular particle, omega is the angular velocity in rad per second, and small r is the distance from the center to the of the rotation, distance center of the rotation to the particle. Okay, that means, remember, particles are moving about an axis. Okay, and here from the distance of the center to the particle is known as r. So omega square r here is the centrifugal acceleration that ultimately provides us that centrifugal force m omega square r. Okay, so this centrifugal force is at the downwards. Okay, but that means, suppose this is a tube. In that tube, this is our sample, so our direction of the centrifugal force will be downward. Okay, but as it is in a liquid, so there will be a opposing bouncy force. Okay, that prevent our particles from sedimenting, so it is working on the upwards. So the formula of bouncy force is m0 omega square r. Okay, so m0 is the mass of the solvent displaced by the particle. So what is the meaning of displacing? So suppose it is your tube and here it is the solvent, so it is our solute and in the solvent. So the, if I zoom that picture, okay, suppose this blue, okay, now I think you can visualize it. So these red dots are the samples. Okay, now these samples are occupying a particular part of the solvent, isn't it? So the mass that is displaced or occupied by the particles is known as m0. Okay, so that is the reason why bouncy force is working on the particle, and the formula of bouncy force is m0 omega square r. So in place of m0 we will put m v bar rho into omega square r. So rho is the density of the solution in gram per milliliter, and v bar is the partial specific volume. Okay, that is the volume occupied by each gram of the solvent, or each gram of the solvent, not solvent, each gram of the solute. Okay, each gram of the particle occupied in solution, that is v bar. So the buoyancy force formula is m v bar rho omega square r. Okay, so as centrifugal force is acting on the downwards and buoyancy force is acting on the outwards, so here will be a net force, right? So if the centrifugal force is in higher amount than the buoyancy force, then the net force will working on downwards, right? And the value of the net force will be m omega square r minus m v bar rho omega square r. So by taking m omega square r as common, we can get m omega square r 1 minus v bar rho, isn't it? That I have written here. Okay, now a frictional force will be working at the opposite side of the net force. Okay, so this frictional force is Vf, as our particles is moving through a solution, so definitely it will observe some kind of frictional force that it is observing. So the capital F here is equal to Vf. So F here is the frictional coefficient and V is the sedimentation velocity, and frictional force will be at the opposite direction of the net force. Okay, so at steady state condition we can tell that the frictional force will be equal to the net force and the particle is moving downward the solution. Okay, so by taking frictional force is equal to net force, we can get Vf is equal to m omega square r minus m v bar rho omega square r. Okay, now we can replace small m by capital M by n. M is the molecular mass of the particle and n is the Avogadro's number. So what is the difference between molecular mass and the normal mass or actual mass? So it is molecular mass is often known as molecular weight of the solute in gram per mole. So that means, suppose you have that I have written here, that is the molecular mass, or you can say the capital M of CO2. Okay, or you can also say it is the molecular weight, that is written often as gram per mole, that is the capital M. But say in reality you have only 4 gram carbon dioxide, okay, then it will be your small m. Okay, that means capital M or molecular mass or molecular weight, which is expressed in gram per mole, it is again a standardized value, nothing more than that. Okay, so now, and n is our Avogadro number 6.022 into 10 to the power 23, that is our very common to us. I am not repeating this anymore. So now by getting that formula, we can easily find out what is the equation for the ratio of sedimentation velocity or rate of the velocity to the angular acceleration or centrifugal acceleration. Okay, so this ratio of the sedimentation velocity to the centrifugal acceleration is known as S, that is our sedimentation coefficient. Okay, I hope you have get this, what I have explained it here. That is, in the solution, suppose you have a molecule A in which your centrifugal force is working, as you have spinning your tube in a centrifuge, then your centrifugal force will working at the downwards, and the value of that centrifugal force is m omega square r, and as it is occupied is some portion of the solution, so a buoyancy force will also be working on at the opposite direction. This buoyancy force is m v bar rho omega square r. Here actual formula is m0 omega square r, that is the mass of the solvent occupied by the particle, but here we are replacing it with the our m v bar rho, because the mass of the fluid displaced by the solvent particle or occupied by the particle is not a joke to measure without any formula. So the m0 is equal to m v bar rho, we have replaced this with that. So now this centrifugal force and buoyancy force will together generate a net force, that can be centrifugal force minus buoyancy force. If that is, then particle will move towards the bottom, and if it is not, that means if buoyancy force is higher, then particle will not move. Okay, so now this net force is the force that driving the molecule towards the bottom. Now as it is moving through a solvent, so obviously it will observe a frictional force that will obviously at the opposite direction of the net force. So the frictional force is Vf. So in steady state condition, the Vf will be equal to m omega square r minus m v bar rho omega square r. Then by taking m omega square r as common, we can get 1 m omega square r 1 minus v bar rho. Then from that we can calculate the sedimentation coefficient. Okay, so sedimentation coefficient, the definition of the sedimentation coefficient is very important for the university exam purpose. So it is the ratio of the velocity to the centrifugal acceleration. Okay, so now there is another term that I want to mention you, that is Wedberg they can ask you what is Vedberg. So Vedberg is when the sedimentation coefficient is 10 to the power minus 13 second, then it is known as Vedberg. Another thing that I want to mention, that sedimentation coefficient is expressed in terms of second. Okay, so that is the idea. A sedimentation coefficient of 10 to the power minus 13 second is known as Vedberg. Okay. So now another thing that is very important from that section, that is what are the conclusion from the principle of the centrifugation. So first conclusion is the sedimentation velocity is exactly proportional to the molecular mass. Okay, a particle with larger molecular mass will sediment faster than the smaller one. Okay, another one is the dense particle will exhibit less buoyancy.